So this is our fourth and final lecture in Chapter 5 on transient conduction. Today's a little bit of a review, but the meat, the brand new material, is down here in section 510, dealing with how to numerically solve a transient conduction problem. We're only going to use the finite difference method. Basically, maybe you go back and look at it, it's Euler. That's the way I learned it. Euler discretization of the time derivative. And then you can have an explicit or implicit method or a Crank-Nicholson or a Runge-Kutta. All those are in the numerical methods class. But we're only going to cover the explicit, how to numerically solve a transient conduction problem. But to start, we're going to do a little review. Here's a review problem. So we have a slab of steel, stainless steel. The slab has thermal conductivity given, K, has a specific heat given, and the mass density given. And it has a thickness of 20 millimeter. And initially has a uniform temperature. T initial is everywhere. I'm going to change that. I think it's 70 degrees C that I'm running with. And is insulated on the left side at x equal to 0. So we'll have an x-coordinate system go from 0 to L, where L is 0.02 meter or 20 millimeter. And it's well insulated over here at the left face. And on the right face, it's abruptly exposed to a convecting fluid where T infinity is given to be 20 degrees C. And a convection coefficient of 450 watts per meter degree C. Okay, that's our problem. And it asks to solve for the temperature at x equal to 0. Where's that? That's way over here on that left side. At a time of 50 seconds, using the lumped capacitance method, which is covered in sections 5.1 and 5.2 of this chapter, which we've already covered. So, can you do that? What would be the strategy for doing that? That's right. That's you can check the BO number, but because they said use it anyway, you know that if it's not small, that just means it's not as accurate as other methods. So let's check the BO number. It's H and our characteristic length for this problem over K. So first clicker question, characteristic length. Is the characteristic length for this problem, is it equal to L over 2, L or 2L? Answer A, B, or C. There was a simple relationship for the characteristic length. It's the volume to area ratio. And so what is the volume of this chunk of material? I know it's a slab, but wouldn't it be this thickness L times some sort of area going back like that? Okay, and those areas are going to cancel because it's L times area. And then what does this A mean? That's the convective area. And do you have any convective area on both sides or one side only? One side only, and so that's the answer, isn't it? So, all right, one way out here. So now that we know what it is, can you calculate a numeric value for the BO number? And so what do you get for the BO number? 450 for the H, 0.02 for the L, and the K is 15. What does that come in at? 0.6. Is the lumped capacitance method justified? No, but you can still use it. It's just that it's not going to be as accurate as the other method we're going to use in a minute. Okay, but let's use the lumped capacitance method and solve this problem. We know it's not justified, so it's going to have some greater error. So how do I find that temperature? Isn't it that the theta, the temperature difference divided by the temperature difference initial, or T minus T infinity, divided by T initial minus T infinity, is equal to, and there's a couple ways the book writes this, EXP, the exponential of minus H A T divided by rho CV. That's a great way of writing it. They also write it as EXP. Didn't leave enough room. E to the minus BO times Fourier. You can also write it like that. There's a couple ways to write this. Professor, is this volume to area ratio what we just worked out? It is. It's the same volume to area ratio. Do you mean that I can replace this? Let me write it like this. T is equal to T infinity plus T initial minus T infinity times the EXP, the exponential of minus H divided by rho CLT. Yeah. And for this problem, what should you put in there for L? I'll ask another clicker question. Should you put in there for L 0 or 0.02? Answer A or answer B? Because it asked you to solve for the temperature at x equal to 0. Everybody got theirs in? Well, so why would some students think that they need to put x equal to 0 in there? Because I know it says I need to find the temperature in the middle where x is 0. That's why they would think that way, but it's not. In the lumped capacitance method, does the lumped capacitance method give you the ability to calculate temperature only as a function of time, or the temperature is a function of both location in this lab as well as time? Just the first, right? And so if you sketch the temperature profile in this slab, because the BO number is, it's higher than, let's say, 0.1, I would expect at some instant in time, it would have some high value, some low value, and then maybe the fluid value out there, right? And so the lumped capacitance method is going to give you a pretty good approximation of the average temperature in the slab, a single value. The actual value out here at the surface will be lower. The actual value in the center will be higher than the single value temperature that the lumped capacitance method predicts. It's 0.2 that goes in there. Now, did some people run this number? And what do we pick up for the temperature at 50 seconds? The average temperature of the slab at 50 seconds. So when we fix this up, this initial temperature is 75. Sorry, but I'm going to run now for the rest of the problem to be 75 for the rest of the lecture. Okay, so this comes in at 59.6 degrees C with the initial temperature 75. Okay, now here's a clicker question. The lumped capacitance method. How does the temperature at x equal to 0 for this problem compare to the temperature at x equal to L at the same time of 50 seconds after, the change in the boundary condition? Is the temperature at 0, 50 greater than the temperature at L, 50? Or is it equal, or is it less? All right, so this question really was a restatement of what I had in red right here, right? So we back up and we look at this question again. From the what is in bold there? From the lumped capacitance method. Not the actual physical reality that the world is behaving like, but the approximation known as the lumped capacitance method applied to this problem. Can the lumped capacitance predict the temperature at a location and time, or does the lumped capacitance method only predict the temperature at a function of time? B. He's learning. Right? So, can the lumped capacitance discern between x equal to 0 and x equal to L? Just grade it. How come I don't have 100%? They're the same temperature. They cannot have a different prediction. It's incapable, not capable of predicting a temperature at the center versus the temperature at the edge being different. It would predict one average temperature, and it'd be a good average temperature for that slab. All right. Somebody says, not good enough. That was in chapter 5.1 and 5.2. We learned the lump capacitance. Then we went to 5.4 and 5.5, and we learned about an analytic technique that had a series solution. So we could get it very accurately. So we could solve for the temperature as a function of both location and time in this slab. So we asked the question, using that method, using the analytic solution method technique covered in that section of the chapter, what is the temperature at the x equal to 0 location at 40 or 50 seconds? And this temperature right here, uniform of 75 degrees C for the uniform's temperature. How would you solve that problem? Should I give you a minute? We're going to check the Fourier number, and if the Fourier number is less than about 0.2, then we only need the first term in the analytic sum of the. Otherwise, the analytic has an infinite series, summation of infinite number of terms. And when you check the Fourier number for this problem, I forget what it comes in at, but it's alpha, which is k divided by rho c. Alpha t time is 50 seconds. Divided by L squared, L is 0.02. Did anybody run the Fourier number? What do we get? I think 0.5 is better. Okay, so good, 0.55-ish, somewhere in there. Okay, so what does the single term look like? It looks like textbook has some theta asterisk, which is the same temperature minus T infinity divided by T initial minus T infinity. Is that the start of the equation we use for lumped capacitance? It really is. It's just this time, if you really wanted to expand it, this temperature would be a function of location and time, not just a function of time like the lumped capacitance. Okay, let's continue on. If you have only the first term, it has that C1 coefficient. It has the exponential of minus this Greek letter, what is that, zeta 1 squared times the Fourier number. Glad we already calculated it, 0.55 or something like that. Keep all those digits in your calculator for that Fourier number. Times the cosine of the same zeta 1 times x asterisk. Okay, so this Fourier number is a dimensionless time. Sometimes I'll write it as t asterisk. This is dimensionless space, x divided by L. If you're evaluating it at x equal to 0, what is x asterisk equal to? 0. What's the cosine of 0? 1, so that term's easy. Okay. The Fourier number, you would run that, put it in. Where do I get the C and the zeta? The table. That's right. And so you need that table in the textbook. I forget, is it table like 5.1? You're given the BO number. The BO number was 0.6 for this problem. You read across, you find a zeta, and you find a C. I forget their values. But in the interest of time, you plug in that zeta and that C from the table, and you're able then to unravel and get a prediction for the temperature at x equal to 0 at time equal to 50 seconds for this problem, and it comes in at 65.3 degrees C. All right. The lumped capacitance gave us temperature only at time equal to 50, and it was 59.6 degrees C. What do you think the temperature at x equal to L is, T equal to 50? Let me do this. I think it's on the next page. Let me go there and ask a clicker question. All right, using this analytic solution method, first term only, how does the temperature at x equal to 0 compare with the temperature at x equal to L at the same time of 50 seconds? Is it greater, equal, or less? So, the temperature out here at L is lower. It's less than the temperature at 0. Isn't it? Yeah. So, I know a lot of these plus, minus, greater than, less than, it's always hard to track it, but there you go. A lot of you got that correct. Oh, what is the temperature out here then? It's less than 59.6. It comes in at 54.5 degrees C. If we go back at our analytic equation, all of this, the C is the same. The exponential of the zeta and the Fourier number, it's all the same. The cosine, but this time, it's not the cosine of 0. It'll be the cosine of x star equal to 1 out there at L, right? So it'll be the cosine of zeta 1. And zeta is in radians. Make sure your calculator's in radian mode, right? Okay. And then it'll come in at 54.5. The last method, finally, what's new today, is a method called numerical finite difference. It's just like what we did for conduction. But what we want to do is we want to solve a transient conduction problem using 5 nodes in our mesh, and we use a time step of 1 second. And we march out 50 time steps to get out to 50 seconds. If each time step is 1 second, and I need to get out to a final time of 50 seconds, the number of time steps is 50. That's what we're going to do. Okay, so what you have to do is you take your slab, it goes from 0 to L, and we have to put 5 nodes. You can put them in a crazy location, but what's going to be the easiest? You're going to put 1, 2, 3, 4, 5. Professor, engineers are kind of boring, aren't they? Look at that. That's kind of a boring mesh. Good. I'm glad it's a boring mesh. Now, what you're going to do is you're going to discretize. Let's call these numbers node number 1, 2, 3, 4, 5. And we're going to solve for temperatures at each of those locations at 50 different time steps until we get out to our final time step. Perfect for computers, terrible by doing it by hand. Yeah, it's perfect for a computer though. Okay, so when we discretize, we come in and we cut. We cut in between. We cut in between. We cut in between, and we cut in between. True? Yes. And now, can you tell me a little bit about the volume associated with node 2 compared to the volume associated with node 3? Is it greater, equal, or less? Answer A, B, or C. I'm looking at the volume in my mesh associated between node 2 and node 3. Do they look like one is greater than the other? Which one's greater, or are they the same magnitude? Yeah, if there's 5 nodes and L is equal to 20 millimeters, what is the distance between the location here and the location there? What is that delta X equal to? Isn't it 5 millimeter? Yes, sir. Let's go back and grade this one now. Very good. The volume associated with node 2 and node 3 are the same. There's no reason that there'd be any different. Okay, now the harder question. I want to compare volume of node 1 with the volume of node 2. Where's node 1? On the insulated boundary. Where's node 2? In the interior. So the same clicker, which one is it? Is volume associated with node 1 greater than, or is it equal, or is it less? Let's do this. Let's say somebody changes the problem and they say, I don't really want to run from L from 0 to 20 millimeters. I'm really going to cut my mesh, and my new mesh goes like this. I'm going to cut right through node 2, and then this is my new insulated boundary right there. So L really has been effectively reduced. It's been shrunk. It's not the full 20 millimeters anymore, right? Now, if that's true, what happened to the volume associated with node 2? It got cut in half. Didn't it get cut in half? Yes. So let's grade this. They are not the same, and volume of 1 is less than the volume of 2 because it's half of the volume of 2. Let's now write an energy balance for the first node, second node, and go through the mesh. So where is node 1? Right here. Let's write an energy balance for it. Let's write our conservation of energy equation. It would be the rate of change of the energy for the control volume associated with node 1 with respect to time is equal to the rate at which heat's flowing into the control volume. And I'm going to say from 2 into 1. And is there any other way for heat to show up? Well, if we had a volumetric heat source, that I'd multiply by the volume associated with node 1. But is there a volumetric heat source in this problem? No. So there's no volumetric heat source. So is that it? Is that my energy balance equation? My transient energy balance equation? Yes, it is. And so how is this energy represented? Well, you've got the energy is the internal energy, which is the mass times the specific heat times temperature, right? Or you could write it as rho C V T, and then you're going to do the time derivative. Is the mass or the density or the specific heat or the volume changing with time? No. So the derivative only lands on the temperature of node 1 with respect to time. And we have the rho and the C and the volume associated with node 1 outside. And then we have this rate equation. Well, how does it flow from 2 into 1? By convection, conduction, or radiation? Conduction. What's our basic discretized Fourier's law look like? It looks like a K, an appropriate area over an appropriate length, times the temperature difference driving the flow, T2 minus T1. Now at this point, we follow what is commonly used in engineering. We have a temperature and we have it at different nodes. So on the subscript, they put where its location is. Oh, it's T2. Oh, that tells me it's at node 2, T3. Or even they had M comma N if in a grid, like location M on the X gridding and N in the Y gridding. Okay. But here, they run out of subscripts. It gets confusing. So they use this superscript, not a power, but a superscript for the time level. Because we're going to have time stepping, right? So if somebody said, this is the temperature of node 2 at 5, well, it would be the 5th time step. Starting where the temperature of node 2 is 0, that would be like initial. And then temperature node 2 after 1 time step, then after 2 time steps, 3 time steps, etc. So you'll see this temperature at location I level P. And then you'll see temperature at location I level, temperature at location I level P plus 1, the next time step, the next time level. This is used in a lot of textbooks. Okay, so what they do is you discretize this time derivative and you put the temperature at location 1 minus the temperature location 1. What you're really doing is it's at the future time divided by or subtracted from the current time. So it's P plus 1 and then this is P. So that's p plus 1, p. This is just a straightforward discretization of that time derivative. Okay, let's put rho c v1. Over here, we're going to have the k a over L. And now we have a choice, T2 minus T1. We could put them at the P level, or we could put them at the P plus 1 level. Professor, what's the difference between this section 510.1 and 510.2? One is the explicit method, one is the implicit method. That's exactly right. What we're doing right here is that we're not going to make it implicit, we're making it explicit, meaning using the current temperature values, we discretize and get the value at the future time step. So it goes something like this. It goes that the temperature 1 at the future time level is the temperature 1 at the current time level plus, you'll have this K A over L rho C V delta T all times temperature 2 at the current time level minus temperature 1 at the current time level. And yes, you can combine this one and that one a little bit more, but let's leave it there. But this is our explicit forward differencing or something like that. It's Euler method. Maybe you learned it as a different name, but you can flip through your textbook and find it. Make sense? So this allows me to move up in time levels for node 1. Guess what we have to do it now for? An interior node. Node 2, node 3, and node 4 are going to look alike. And then we have to do it for node 5 because it's a convective boundary condition. And you have to get these equations right before you implement in your code. Did everybody write that down, or do I need to go back? Go back a little bit. I guess what I could write or work on is this area and then this volume. Okay, so think about it now. This volume of 1, the volume of 1, isn't that some sort of big area going back times delta x over 2? Is that right? And that big area we usually just pick to be 1 meter squared or 1 something. It's just as, because we just normalize it. And that's the same as this area right there, so it cancels. And so this term of K A over rho C L V1 delta T turns into something like K delta T divided by rho C L, okay, that L is delta X, and then V over A is delta X over 2. I mean, this L right here, this L right there is delta X. It's this distance. But the volume is, for volume 1, is delta X over 2 times whatever area is in the third. Yes?
Why doesn't the conduction have the negative sign?
Yes?
I have 2 questions, Dr. Mantoical. So, why do you eliminate the Q dot times the volume?
There's no heat source. No electrical type of or chemical type of or nuclear type of heat source.
So, like, how would it look like in order to include the... So it would have to have a heat source?
Yeah, in this problem we don't have a volumetric heat source. But I show it in case you do have a problem where you have volumetric heat source in it, where it would come into the energy balance equation.
Like, what kind of keywords should we look for in a problem?
Electrical resistive heating, then that's a 2, then rho C delta X. This L right here is a delta X. This V is a delta X over 2 times the area. Those areas cancel. Now the next one, the interior one, like for node 3 or node 2 or node 4, is pretty easy. So let me jump to the hard one, or do you want me to do the easy before the next hardest? The next hardest is 5. with the convective, because you have convective out here. Which one do you want to do first? Go to 5. All right. So here's the convective. And so what I'm thinking is don't forget that this distance for the volume of 5 is delta x over 2 times that area of 1 meter squared. Just pick a 1 meter squared, make your life easy. Okay. And then we have the flow from 4 into 5 and the flow from t infinity into 5. That's the way we're going to write it. So what we do is we have rho c, then we have the volume of 5. I'm going to replace the volume of 5 as delta x over 2 times the area. The time rate of change of the temperature at 5 is equal to, then we're going to have a k. The area is just the regular area for flow from 4 to 5, but the length is delta x, then temperature 4 minus temperature 5. That's our conduction from 4 into 5. Then we're going to have an h times the same area times the temperature infinity minus the temperature 5. And yes, that area, that's why I just pick it to be 1 meter squared. It will cancel out of your equations if you write the equations correctly. Yeah. All right, now we're going to put a time level of P and P and P and P, and we're going to replace this time derivative by temperature at 5 at P plus 1 minus temperature at 5 at P divided by delta T. So this comes rho C delta X over 2 equal to K over delta X, T4 at P minus T5 at P, plus H times T infinity at P minus T5 at P. Take a full sheet of paper, go slow, take more baby steps as you develop confidence in what you're doing, and then you'll have temperature at 5 at P plus 1 equal to temperature at 5 at P equal to, or plus, and then we're going to have this kind of craziness here. K divided by rho C delta X squared 2 times, I forgot that delta T. I always forget that delta T. Delta T. All right. Times T4 at P minus T5 at P plus H divided by 2 delta, or times 2 delta T divided by rho C delta X T infinity at P minus T5 at P. I think I did it all right there. Did I make a mistake or not? Does it look okay?
What is that first subscript at the top of the T5?
P plus 1, yeah. So at the future time level, and it only depends on the values at the current time level, at the P level. Now, once you have all the equations, you have to put it in MATLAB, or you have to put it in Excel, or Python, or C, or C++, or Fortran, or BASIC, or something. So in the interest of time, let me just show you kind of what it looks like in Excel. So over here, what I did was I put in a lot of values which are the input parameters. What is the T initial? What is T infinity? What is H? What is K and rho and C and alpha? And what's the time step size, 1 second? What's the space step size, etc. And then I calculated some parameters which you're going to use to code up. So over here, I have different step, like step 1, step 2, step 3, step 4, and this is the actual time. If in Excel I decided to say, well, the time step, so once you set it up in the computer, it's nice because let's say, oh no, I want to run with a time step of 1.5 seconds. Well then, 1 step brings me out 1.5 seconds, and then it's 3 seconds, and 4.5, then, see what I'm doing? Or they say, oh no, I want you to run with a time step size of 0.5 second, and then so the number of steps versus the time is there. So let's go back and just solve it for 1 second time step. So it kind of looks funny that 1 is 1 and 2 is 2, etc. But here, node 1, node 2, node 3, node 4, node 5, and then the fluid. And I just put the fluid in here as an extra node, and it doesn't change. It's always 20. But they start at 75, and at 1 second, I guess I'm off by 1 second. This should be minus, it should be this. Sorry about that, I'll fix it. Go like this, minus 1. Because it starts at time 0, and then it goes 1 second, 2, etc. So this is the initial conditions right there. Put them in bold, or I don't know, some other color. And then they start marching. Notice it takes a while before the interior node at 1 starts to change temperature, doesn't it? It doesn't start changing temperature till like 7 or 8 seconds. But that's the way it goes. It takes a while for it to propagate. And then you start marching. Now you go down here and go down and go down, and this is now 49 seconds, so I need to drag down one more. There. So my actual answer is 65.4 at the x equal to 0 and 54.5 at x equal to L. Bold. Because that's the solution at time of 50 seconds. Hopefully that makes sense to everybody. So when you code it up in Excel, if I clicked for this one in cell 3, it basically uses the previous time step values and some parameter that's over here, and then it predicts it, and boom, that's how you code it up. And like here for node 1, it just uses those two at the previous time level. And then over here at the node 5, just uses this one, and the fluid level, fluid node. And so you have to get the equations right, code it up, and then solve. Somebody says, look it, I really want to do this with a time step of 5 seconds, right? Hey, what's this? Hey, what is that? Hold it, 75, 75, 75, 58, 125, negative 114, 622. Professor, you're teaching us garbage. It only works when it's 1, and it doesn't work if I put in a time step of 5. In numerical methods class, there's a thing called stability of your algorithm. And explicit methods are notorious. They have stability limits. You can't get too large of a time step. If you get too large of a time step, it starts to oscillate numerically, and now it's bouncing around. And the book has a great discussion of it, and I know it's in the Chapra and Canali textbook that you use for numerical methods. And I point that out because sometimes, you'll run a problem and you'll get garbage out, but it's not because any parameter was garbage, it's because the numerics are such that it's unstable algorithmically. So, anybody ever experienced this in practice? Did you solve any problems and see that? Well, here you go. So you see it where I coded it up, but it's nothing like coding it up yourself. When in doubt, cut your time step, cut your mesh size, increase the number of nodes, number of time steps, and then converge to a solution. All right, well, with that, let me see if there's any other questions I have for you. The values are pretty close for the analytic and the numeric solution. They're very close, actually, okay? The lump capacitance is in, it doesn't discern between the surface temperature and the centerline temperature. It gives you a good average temperature. So with that, I thank you for your attention. We're done with this section of 510. The most important, lump capacitance, the analytic solution. It's going to be hard to give you a test problem. I may try. It's pretty hard to give you a test problem on the numerical method stuff. Thank you for your attention.